Hey guys, welcome to Wired to Learn, and this is going to be episode 2 of our Intro to Chemical Engineering series. Today we're going to be talking about process variables and linear interpolation. So, in this lecture, we'll deepen our understanding on how chemical processes are defined and measured. We will review fundamental process variables, differentiate between process types, and solve basic interpolation problems, which are going to be essential for working with real world data for our real engineering problems. All right, so to go ahead and dive on in, chemical processes can involve single or multiple unit operations. They may operate in batch mode, where materials is processed in discrete quantities, or continuously, where inputs and outputs flow nonstop. Your batch processes are going to be like baking cookies. You're going to put your materials in, you're going to let them react, and then after a certain amount of time with a complete reaction, you're going to take them out and you'll have your finished product. Whereas on continuous, your inputs and outputs are always happen simultaneously. They're not stopping, and you're going to have one constant flow or it's going to be steady state. So to carry on from last episode, we described chemical processes using variables like composition and flow. Composition can be expressed as a percentage by mass, moles, or volume. Your flow rates may be volumetric, which is liters per minute, mass based, which is going to be kilograms or pounds per second, or even molar, which will just be moles per minute or second. So, so understanding mass in moles is going to be fundamental throughout your career. The mole concept connects mass to molecular weight. For instance, 1 mole of water weighs 18.016 grams. This is going to be important for whenever we're, doing reaction in moles and then transitioning to find out how much of that product it actually is in pounds or kilograms. And as for your mass and mole fractions, they're always going to be simple ratios and always going to sum to 1. They're used to calculate average molecular weights or component properties. So as for molecular weight, you won't have to deal too much with it just by knowing what the molecular weight is so you can convert. But density, volume, specific gravity, these formulas will start to come up more. You're going to start to find yourself being able to work very fluently with them as you do more and more problems. But to calculate the average molecular weight of a mixture, you're simply just going to divide the total mass by the total number of moles. And for density, density is a mass per unit of volume, and the specific gravity is going to be the ratio of the substance's density compared to water. So you're always going to use water as your reference for specific gravity. The unitless quantity is often easier to use in calculations. So specific gravity is often easier to use than density sometimes. There's many times that we work with concentrations. We work with concentrations in numerous amounts of problems, but concentration can be expressed in many ways. In environmental or trace analysis, ppm or ppb, those are some of the common ways. But in solutions, your molarity is going to be widely used. But in industry, sometimes ppm is going to be used if depending on where you're working or what kind of problem you're kind of deal with. Flow rate measurements are also critical. Volumetric flow is commonly measured, and then it's going to be converted to mass flow using the density. Devices like rotometers are used to measure flow, and there's a few other, flow rate measurements out there in the industry. You just kind of don't need to know them at the time. If you get into design, you may need to get into learning what the other measurement devices are. Now, talking about pressure. Pressure is a force per unit area. In practice, we use gauge pressure, which is pressure relative to the atmosphere. But sometimes we work in absolute pressure, which is basically your gauge pressure plus your atmospheric pressure. I have this formula down below where it kind of shows you how absolute pressure is going to be your total and your gauge pressure is going to be kind of what you see on a gauge out in the industry. But you always, if you're going to work with an absolute temperature, you're going to always have to add your atmospheric pressure in there. So taking a dive into interpolation, Interpolation helps estimate values between known data points. The 2-point formula assumes a linear change between the 2 points. These are going to be helpful whenever we're taking data off of steam tables or any table, whatever we're using for reference. It's going to be able to take a point that was not determined in the lab, and we're going to be able to use and estimate what that value may be based on the data that we do have. So to go ahead and work a problem on interpolation, we may be told to estimate the internal energy at 3 degrees Celsius. So right here it says estimate U at 3 degrees Celsius. So U is going to be our internal energy. So basically what we're given from our tables is going to be, we have the internal energy of water at 2 degrees and 4 degrees, but we need to find what's in the middle of it. So for the first step is going to be our first data point, which is going to be T1 at 2 degrees Celsius, and the internal energy that's correlated with that temperature. And then we're going to find the second data point, which is for the second temperature, which is going to be 4 degrees, and also the internal energy with that temperature. And so we're going to basically let T1 and U1 be X1 and Y1, and then X2 and Y2 be for the second temperature and the second internal energy. And our X will be our ideal value for our temperature, and then Y is going to be what we need to find. So basically, it's just going to be a plug and chug. We're going to plug these values into our formula and get a solution. So you may not be good at this at first, but the more problems that you work, you're going to get the better and better. So I'll try to do a video on working more and more problems. So today we lay the groundwork for analyzing chemical processes and understanding these variables and how to interpret data, which is essential as we progress through the course. In the next episode, we're going to learn how to represent entire processes using flow diagrams, which is going to be a vital skill for chemical engineers. So be sure to tune in, give it a like if you enjoyed the video, if you thought it was helpful, and be sure to subscribe and follow if you're going to follow the episodes. All right. Thank you all and see you on the next one.